Hello, my name is Simon Joe, and today I would like to go over question 18.6 from homework number 2 with you. I apologize for my messy desk. Got a check here, realized that rent was due, but also Pencast is due, so gotta make tough choices here. And so let us get started. As you can see from the drawn diagram, we are trying to find the phase constant for a snapshot graph of a sinusoidal wave traveling to the positive direction at 1 meter per second at a time equal to t equals 1 second. Now if you are a smart person unlike me, you would have probably realized by now that you could just draw a standard sine wave with no phase constant and make the comparison from there. And we see that the resulting shift from standard sine wave is a half pi shift to the left, or negative half pi. But if you like it long and painful like me, you'd realize that there is an equation made just for the sine wave with the phase constant incorporated right into it. The displacement equation for a traveling sinusoidal wave. So let's start filling in the variables. First with k, the circular wave number. This can simply be found by taking 2 pi and dividing it by the wavelength of the sine wave. What is the wavelength, you may ask? Well, that would be easily found by measuring our sine wave graph from peak to peak, measuring up to 2 meters. And so by plugging 2 meters into our wave number equation, we find the wave number to be 2 pi over 2 meters, or pi over meters. Next, we find our angular frequency, equal to 2 pi times the frequency of the sine wave. The frequency of our sine wave can be found as the velocity of the wave divided by wavelength. Plugging this into our angular frequency equation, it is found that the angular frequency is equal to pi over seconds. With both wave numbers and angular frequencies found, we can now plug these into our original equation. Since it was given in the problem that the time the snapshot graph was taken was at t equals 1 second, we can allow t to be replaced by 1 second. Now as for x, we can simply choose an x-coordinate on our sine wave graph. I chose x equals 0 for simplicity's sake. Let's plug in x and simplify this equation. One last problem with this equation is what might d, or displacement, be equal to since it's not given in the equation? Well, since we chose 0 to be our x-coordinate, where the amplitude is the greatest, we can assume amplitude is equal to capital A, or the maximal amplitude. Substituting d for a in our equation, we see that we can divide both sides by a and simplify this equation further. And now, we are left with a much better equation to work with. 1 equals sine of negative pi plus our phase constant we are trying to find. So let's take a little step back and check. Sine of what radians might be equal to 1? Well, that could be an infinite amount of numbers, but we will choose to stick to as simple as possible. Sine of both half pi and negative 1.5 pi are both equal to 1. So whatever might be within those parentheses next to sine will have to be equal to half pi or negative 1.5 pi. Both half pi and negative 1.5 pi will result in an answer that will work, and I will show the answer this time using negative 1.5 pi. And so, by simplifying our equation, we find our phase constant to be equal to negative half pi, as we saw in the quick method of comparing sine waves. Thank you for watching my Pencast, and I hope you have a wonderful day.